Hello and welcome once again for another episode of Daily Differential Equations. This time we're going to discuss solving simultaneous differential equations. And there's a couple of methods that we could use, and we'll get into other ones in a different video. But this one I'm going to do by substitution. Another popular one is elimination. By substitution, I think is a fairly straightforward way of solving these kinds of differential equations, though. So I have this set of simultaneous differential equations. Dx dt is equal to 2x minus y, and dy dt is equal to x. And then we're going to use the notation that d, the differential operator in this case, is going to be d by dt. Okay? And we're going to see that using the differential operator is a pretty powerful technique to solve differential equations. Linear. This is, by the way, this is a set of linear first-order constant coefficient differential equations. So we can use this method in this scenario. So I'm going to write it in differential operator form first. So let's put it, I'm going to do that in blue here. So dx is equal to 2x minus y, and dy is equal to x. Pretty simple. And then I can actually, the beauty of using the differential operator is I can actually do regular algebra with it. So dx minus 2x is equal to minus y, and I could think of d almost as if it was, say, a coefficient. So that's what I'm going to do. I'm going to use it as if it's a coefficient. D minus 2 times x, so I can factor out the x now, is equal to minus y. And that means that x is equal to minus y divided by d minus 2. So now I'm going to be able to substitute it back into the second equation, this equation up here, for x, which is what I'm going to do. And when I do that substitution, I get dy is equal to minus y divided by d minus 2. And if I multiply by the d minus 2, I multiply that through, I get d squared y minus 2 dy is equal to minus y, which I can then obviously add the y over. And now I get a second order linear constant coefficient differential equation, which we know how to solve, right? So what we do with these kinds of differential equations, as you probably know at this point, is we suppose that y is equal to e to the rt, then y prime is going to be equal to r e to the rt, and y double prime is going to be equal to r squared e to the rt. And I can then substitute in these things. So obviously for y double prime, I'll put in r squared e to the rt, for instance. This will be minus 2r e to the rt, and so on. And I'm going to because you're going to notice that all three of these are going to have an e to the rt in it. So I'm going to factor that out immediately, which is what I do here. So now it's factored out. I get r squared minus 2r plus 1 e to the rt. And the only way that this thing on the left-hand side can be equal to 0 is if the part that is underlined here, this part, is equal to 0, because e to the rt is never going to be 0. So now I'm going to factor it out. I get r minus 1 times r minus 1. And of course, since this has the same root, we get the same root twice. To get a set of linearly independent solutions, because of the same e, you get e to the t twice here, essentially. To get a set of linearly independent solutions, I have to multiply one of them by t, which is what I do over here. And I get y is equal to c1 e to the t plus c2 t e to the t. Okay, so now I've solved this, but I only solved it for y, and I could solve it for x, right? So I can go back up here to this part, and now I have my y, so I can use that to solve for x, which is what I'm going to do down here. So remember that x was equal to minus y divided by d minus 2. So that means I can go back to the original form, which is dx minus 2x is equal to minus y, but minus y is equal to minus c1 e to the t minus c2 t e to the t. And so finally I get this equation, which I can solve for x. Now notice that this is a first order differential equation, so that's nice, and we have ways of solving them. But in this case, we can't solve this by separation of variables, right? Because I have this minus 2x here. So I'm going to have to use the integrating factor. So if is going to be equal to, my integrating factor is going to be equal to e to the minus 2 times the integral of dt. Okay? Which is obviously just e to the minus 2 times t. And I can then use the integrating factor, right? So this becomes, after doing the integrating factor, I'm not going to go over how to do that. You can remind yourself. But essentially, we'd end up with e to the minus 2t times x is equal to the integral. And by the way, we've already handled the constants here, these constants, so I don't need to add another constant. So keep that in mind. In fact, I should not add another constant because the constants have already been taken care of. Is equal to the integral, well, I'm going to split this into two pieces. So it's going to be minus c1 e to the minus 2t, because I'm multiplying by that integrating factor, times e to the t. And then minus, I'm splitting it up into dt. I'm splitting it up into two integrals, so minus c2 integral of t e to the t times e to the minus 2t dt. And I like this problem because it's kind of a tour de force here that we're gonna have to go through. So this becomes equal to minus c1 times the integral of e to the minus t dt minus c2 times the integral of t e to the t minus t dt. Okay. And this integral is rather easy. I just end up with c1 e to the minus t. But this integral is not as easy, but I can just use my handy-dandy integration by parts method. So I'm going to let u equal to t, which means du is equal to dt. And dv then is going to be e to the minus t, and v is going to be minus e to the minus t. So, I'm going to have to remember that I have on the outside here, so this is going to be minus, let me erase that and put this in red, minus c2 times, we're going to have uv, so t, this is going to be minus t e to the minus t, minus the integral, which is going to have a minus sign in it because of that. So this is going to end up being plus e to the minus t dt, which is obviously easy enough to solve. So this is going to be equal to c1 e to the minus t minus c2 times minus t e to the minus t plus e to the minus t. And if I work that all out, I get c1 e to the minus t. I'm going to move this part over here, so minus c2 e to the minus t plus c2 t e to the minus t, And I'm going to have to remind myself up here that this was equal to e to the minus 2t times x, and I really want to solve this for x, right? So I'm going to multiply across, and I'm going to get x is equal to c1 e to the t. Actually, let's just do the c1 minus c2, which is obviously a different constant that I could call c3 if I wanted, right? So I could call this a constant, but I'm just going to leave it like this. E to the t plus c2 t e to the t. Because, right, dividing by e to the minus 2t is the same as multiplying by e to the plus 2t. And that gives me my solution here. Okay? So that's my solution for x, and this is my solution for y. Hopefully that made sense to everybody. Hope to see you again soon.